Hello all, welcome back. Today we will be continuing with our topic, that is multi-stage rockets. My name is Sai Krishna from the Department of Aeronautical Engineering, from the Institute of Aeronautical Engineering. Today we will be continuing our course for the aerospace propulsion. Now, in our previous class, what we have discussed is basically the multi-stage rockets. I will just go over a small recap for them so that it will be easier to understand the further more topics that are optimizing of multi-stage rockets, in what way we can optimize the rockets. Now, it is easy to intuitively that the discarding of the empty fuel tanks during the flight and is bound to improve the performance of the rocket, whereas the thrust remains the same, but after the tanks have been dropped off, the mass of the rocket is smaller and the acceleration will get greater. Similarly, and in order to calculate the effect, one can consider a single rocket of given mass ratio, then divide it to two smaller rockets whose combined mass is the same, right? And this we have already discussed in the previous class. I'll just recap a bit. The payload, or in which the part that is to be put under to the place, we are denoting it as MP, M suffix P, whereas and the structural mass as well as the fuel mass are denoted by M suffix F. So, if you are considering as a single initial rocket, you are having an initial mass ratio for a single rocket is R0. Now, same definition as before. Now, the propellant or the fuel mass is distinguished by having the amount of fuel or the oxidizer that it has, whereas MP is nothing but your payload mass. Whereas structural mass, which is denoted by your MS, is basically consisting of your rocket engines, turbo pumps, fuel tanks, as well as the guidance and control systems. Now, in order to maintain this empty structural mass to minimum, we may assume that a constant fraction of your fuel as well as fuel has to be maintained by your structural mass. Now, let us understand the same. If you are considering a single stage rocket, this will be in this manner, where you are having mass of the payload, mass of fuel, and another everything is related to your mass of structures. If you are splitting the same thing under two sections, where the mass of fuel gets halved out, similarly, the structure will also get halved out, but your payload remains same. Now, after certain duration, what happens? After, if you are, let's say, if you are considering this as stage 1 and stage 2, and this is your payload. Now, after certain duration of burning of your stage 1, what happens? That will be an empty weight. Now, so that can be discarded so that your complete mass or complete structural mass gets halved out. So, half will be removed out, whereas other half of the structural mass from your initial stage and total weight remains as it is, along with your half of the fuel. Now, this can be completely given by, in terms of mass ratio for first stage of the rocket, is mass of structure, fuel as well as propellant, which is nothing but my initial, and mass of structure, half of the fuel and half of, complete this one. This will be instantaneous, or M naught by M, as defined in your mass ratio. Now, for the fuel burned in the half single rocket, the lower rocket then drops off and the upper rocket is ignited, which is nothing but discarding of your lower stages. Next, what happens is it gains an additional velocity, which is again given for your second stage. Is in the second stage you are having only half of your structural mass and half of your fuel, right? Because at the initial rocket you are having completely carrying half of your fuel as well as structural mass in your upper stage as well, upper plus lower, right? But after a certain period of time, when you are discarding your lowest rocket, then what happens? This lower stage gets removed off, so only upper part remains, right? So that upper part you are considering it as half of the values. Next, MP is nothing but your payload weight, and ms is the remaining final instantaneous structural weight as well as the payload weight, because at the end you will be consuming all of the fuel. Now, if you're considering the same ratios and putting onto your simple rocket equation, what happens for a rocket having a single stage? You'll be having this equation, which is nothing but initial vehicle, sorry, rocket vehicle velocity is nothing but exhaust velocity and logarithmic of your initial rocket mass or rocket mass ratio. Whereas if you're going for multiple stages, particularly multi-stage, if you're using a two-stage rocket engine, what happens? The rocket velocity will be equals to a logarithmic value of the first mass ratio for your stage 1 and another addition for stage 2. Now, on comparing, we can get a clear idea that the initial rocket velocity or the final rocket velocity for multi-stage rockets are more rather than a single stage rocket, and based on this we will be optimizing it further. Now, previously, what based on v is greater than v naught, we have assumed based on the equal division of fuel among the stages, right? Let's say for stage 1 and stage 2 we are having equal divisions, but by calculations of variations that for equal exhaust velocities and for the same propellants, the optimum velocity increment occurs when payload ratios are staged equal, right? And if the structural efficiency of the stages is the same, then the equivalent to declaring that mass ratio should be equal. We will understand this clearly before going further. Now, and by means, what we are assuming earlier was for stage 1, stage 2 as well as payload. It's the same example that we have considered earlier. The mass ratios, particularly the fuel, mass of fuel in stage 1 is equals to mass of fuel at stage 2. Right? If payload doesn't have any fuel, we are not considering that. Now, by means of some variations, particularly using calculus, and we are calculating for equal exhaust velocities for VE1 and VE2 and the same propellant, and the optimum velocity increment occurs when the payload ratios for the stages, right? The payload ratios are given by L are equal. Similarly, if the structural efficiency denoted by sigma of the stages are same, these are the two new terms we will be discussing further. The payload ratio as well as the structural efficiency or the structural coefficient of the stages are same, then this is equivalent to declaring that your mass ratios are same. Now, let us understand the payload ratio. Now, it means the measure of usefulness of the rocket, and the structural efficiency is a measure of degree of optimization of engineering design, and they are denoted by L and sigma for each stage. And for optimum performance, the mass ratio will also be same for each stage. Now, for example, in a multi-stage rocket, what happens? We'll just go back. Right. Let us see the two-stage rocket engine in a combined form. In a multi-stage rocket engine, if I considering simply, what you are doing, for a single stage, you are dividing into two. Now, for stage 1 and stage 2, this is the final payload that we are supposed to inject into the orbit, right? Now, considering this as my complete payload, let's assume, right, what happens? For the stage 1, it's a complete payload that it's supposed to inject to a certain altitude by whatever the fuel it has as well as the structural mass. It's supposed to consider the structural mass as well as the mass of the fuel. Now, considering both the terms, what happens? The overall mass of the payload is higher rather than what is supposed to be injected. Now, the combined mass is supposed to be, while injecting, it needs the higher amount of velocity increment. because the payload itself is higher, as well as the launcher vehicle, particularly the lower stages, are of low efficiency. So in order to optimize them, in order to optimize a multi-stage rocket, what we are doing, we are using additional high power engines which create higher exhaust velocities, or we add certain systems, certain boosters to enhance the performance of your lower stages. Now, as soon as the time progresses, as soon as, let's say, your lower stage has performed very well and you are discarding your lower stage, next what happens? Upon reigniting your upper stage, particularly stage 2, this will be your final payload, right? Now, in order to drop this particular payload to a certain orbit or certain altitude, the energy required will be less comparatively to your stage 1. Because on stage 1, complete stage 2 as well as stage payload is a complete payload for stage 1. Whereas for stage 2, only the final payload is your actual payload to be inserted into the orbit. Now, for this purpose, the stage 2 is not necessary to have that high amount of thrust and high amount of specific impulse. Right? Let us come back. Now, as discussed, the payload for the first stage is a combined mass of the second and third stages. In our case, the third stage is my payload, particularly a satellite or a launch vehicle, anything else. And the payload for the second is only a third stage, which is nothing but our payload. Now, the lower stages should have a bigger share of propellant. Why? Because as soon we are supposed to create more exhaust velocity, particularly more velocity, in order to push my second and third stage further. So my lower stages should be having more amount of propeller in order to create more amount of velocity and than the upper stages, and in order to the mass ratios to be same, and in order to keep my exhaust velocities. Now, if I are denoting mathematically, the payload ratio for a single stage is denoted by L, is mass of payload to the ratio of mass of structure and mass of fuel, right? And it's for a single wheel. Similarly, for structural efficiency, mass of structure, mass of fuel, and mass of again structure. Let us understand. In this case, everywhere, mass of payload, which is nothing but my final to my initial, particularly in order to inject the payload to a final orbit, what are the initial structural as well as fuel requirements that we require. Based on that, we are providing the payload ratio. Similarly, for structural efficiency, what will the final structure that is available after the complete exhaustion of fuel, right? This will be your initial final, right? The structural efficiency is also called as coefficient. Now, if we are considering these ratios as a simple function of mass ratio, then R can be rewritten as 1 plus L by sigma plus L. Now, and it's convenient to represent the mass fractions for all the three stages as ABCs and respectively. So, the mass ratio for the first two stages R is defined by A plus B plus C, BC, and BC plus by C equals to R. Let us understand this. My stage 1, 2, 3. Or else let's consider it as vice versa. It will be better. My stage 1, which is A, 2, B, C, 3 will be C. Now, this third stage in our what we have considered previously is my payload, or else you can consider another third stage, is not an issue. Now, what happens is for first stage, as we have discussed earlier, for first stage, stage 2 and stage 3 are a combined payload. right? For that reason, what we are considering, if they are fractional masses, the initial mass, what we are giving it as m naught by m. Initially, for stage 1, what will the total mass of the rocket is basically a plus b plus c to the ratio of what will the final mass of the rocket upon completing for your first stage is nothing but b plus c in the denominator. In a similar form, if you are considering for second stage, right? If you are considering for second stage, what happens? This will be the only payload, right? And while considering the initial mass of the rocket, it will be b plus c as denoted to the ratio of your final mass or final mass uh, that is available at the end is your c. Now these we are considering as proportional as equal to my stage r. Now the mass ratios for the third stage. In order to determine the mass ratios for the third stage, we can rewrite the same in terms of proportions A, B as well as C. And in order to find what the basic proportions in which A, B as well as C are to be maintained in order to create a 3-stage rocket engine. Right? In order to maintain a 3-stage rocket engine. Now, for a fair test, what we are doing, the optimization of the value should be determined from parameters from the original single stage rocket. Right? If you are considering a single stage rocket, we are making a small comparison in order to understand in what way that we will be able to identify the parameters. Now, the assumed parameters of a single stage rocket for the same limit is 4.67. That is nothing but my mass ratio R for single rocket. Now taking this as an approximate value, and we are determining the values of A as well as B as well as C. We determine this as 0.7816 as well as 0.004. Now combining these will give you a complete 100% of the mass ratios, particularly mass fractions. Now this particular value, if you are putting under, let's say, percentage value, it will be approximately 78 or 78.4%, and this will be around 16.91%. This will be around 4.6%. Right? Now, what will be able to understand from this is basically whenever we are considering a 3-stage rocket, right? Let me just read it right. Whenever considering a 3-stage rocket, considering the first stage as the ground, towards the ground, second as well as third, the major proportion, right? What we are considering this as A, B, C. Let's say these are stages, right? The major proportion is to be borne by my first stage. It's nothing but approximately 78.4%. Similarly, B will be 16.9% and 4.6%. These are nothing but my mass ratios that we have been identified by considering a few parameters. Now, whenever we are considering, and this holds right basically. How? Because whenever we are launching a 3-stage rocket engine, we are considering B and C as a payload for stage 1, and for stage B, only C will be having a smaller payload weight. Now, this leads, if you are solving more accurately, it will leads to a value of 3.39 as the mass ratio for the stages. We are maintaining 3.39 for each and every stage. Now, each stage now has the same mass ratio. The velocity increment is also gained by the same. So, the total velocity that is being gained by each and every stage is 3 times, or we are taking a value of 3 times 2700, which is nothing but my exhaust velocity, if I am considering it as the same exhaust velocity, and the natural logarithmic of 3.39 as my mass ratio. right? It gives me around 9.889 meter per second. Also can be, sorry, 9.8 kilometer per second, right? Now the total velocity of my three-stage rocket engine would be 9.8 kilometer per second. And comparing the velocity increment for the three-stage rocket engines with the stages of equal mass, we see that optimum mass distribution produces an increase of 1.7 kilometer per second in addition, right? Now, as we have optimized the multi-stage rockets, we are supposed to optimize the rocket engines also. Now, the calculation that we have performed earlier are increasing the number of stages till the 3. What if we are increasing the stages to a 4-stage rocket? Previously what we have done only till 3 stage. Now if you are increasing it to a 4 stage, the only issue is the gain in the velocity increment is not as much as compared to 2 to 3 stages. And the cost and the complexity of each and additional stage, where each stage will have its own engines, own fuel pumps and own guidance systems to operate. Now, a multi-stage rocket therefore is more expensive than a single stage rocket, obviously. Now, whenever we are optimizing the rocket engines, what happens? Let us understand in what way does a rocket travel. Now, a rocket which is currently under lower atmosphere operates in a conditions very different to those in the vacuum of space. Let us understand a bit. Earth, let's say this it is space, you are launching a rocket onto the ground. Now, whenever we are launching a rocket towards space, what happens? If you are considering the same engine, same type of rocket engine, those are efficient to be performed under Earth, whereas in space there are completely different conditions, right? So these are supposed to work under 2 separate areas or 2 separate regimes in which the conditions vary drastically. So at the initial stages of flight, what happens? The atmospheric pressure is high, that is approximately towards the Earth, and it affects the performance of the rocket, whereas the atmospheric drag and other aerodynamic effects are also strong in the low atmosphere. In space, the engines are operated in vacuum and there is no drag as well as slip. Now, the rocket exhaust is strongly affected by the pressure at the exit of the nozzle, and the air pressure retards the exhaust stream. For example, let us consider a rocket nozzle. Now, this will be my nozzle. Now, coming to our point, whenever the exhaust is being sent through, particularly exhaust velocity, gases in terms of combustion products are sent toward the nozzle. What happens at the lower atmosphere or below the space? We are having air, particularly air at atmospheric pressure, which varies accordingly to the altitude, which directly affects the performance of the rocket engine. Now, what happens in our case, basically under rocket principle, whatever the exhaust gases are getting out, the same amount of momentum or the opposite force we are getting from the rocket engine. Now, as in space, there is no atmospheric effects that has to be considered. Now, as soon as the rocket gas expands, right, the surrounding air will try to push in, right? If the pressure of the exhaust is less than pressure of atmosphere, what happens? The air tends to push the exhaust gases towards the center of the nozzle, whereas pressure of exhaust is higher than the pressure of atmosphere, what happens? The exhaust will try to develop itself along a certain area through which it can dissipate its energy. There are some cases in which the pressure of exhaust is equals to pressure of atmosphere. In those cases, it will be following a certain boundary in which the energy is dissipated. Now, these particular conditions are called nozzle expansion. We'll be discussing them further in the module 2, but it's a small concept. Next, and in order to find out optimum exhaust velocity that is low in atmosphere, the exhaust nozzle should be short as well as the exhaust should not expand too much. And for vacuum, the nozzle should be long and the exhaust should be expanded as much as possible. This means a rocket cannot be optimally designed for the whole journey of space, whereas a multi-stage rocket offers an ideal solution to the dilemma. The first stage can be designed for the best performance in the lowest atmosphere, whereas the upper stages can be designed to perform under best in vacuum. Now, this applies to the nozzle length and it can also apply to the type of fuel. Do you understand this? Let's consider the same example. 3-stage rocket engine with my third is my payload, if I'm considering, and let's say the first stage will be working under no. If it's a single rocket engine, for example, let's consider it as a single rocket engine. What happens? I'm supposed to have a single long rocket which burns continuously to deliver my payload to a certain altitude. Now, in my case, what I can do, let's say if I'm considering a multi-stage rocket engine, then I can split it into two, right? Redesign my first stage to overcome my aerodynamic properties, particularly aerospace properties in terms of atmospheric properties. To counter them, I need to have a higher amount of propellant, particularly in first stage. So, I can optimize my rocket engine to work under lower atmosphere and high thrust to overcome my stages. Now, as soon as my rocket passes the lower atmosphere, what I can do? I can ditch my lower stage consisting of my heavy mass of tanks as well as my fuel. I can redesign my stage 2 to perform with better efficiency in vacuum of space, right? In space, I can redesign my second based on the vacuum of space working conditions. Now, in these cases, the nozzle expansion will be depending based on the nozzle length primarily. So, in order to cover up for the nozzle length, any atmospheric gas, particularly in low of the atmosphere, the exhaust nozzle that we will be using should be short, whereas for in vacuum the nozzle should be long enough so that it can maintain the expansion ratio. Now, the same thing can be applied for the type of fuel we are using. Now, the first stage is the task of lifting the rocket more or less vertically through the lower atmosphere, and it needs to have a high thrust because it has to lift the entire mass of the multi-stage rocket, particularly my stage 2 plus 3 or my payload. Right? Now, the upper stages are lighter because as soon as I progress further, I am supposed to discard the lower stages so that my overall structure of the mass or overall mass of the rocket decreases so that my efficiency increases. That is the whole concept of your multi-staging, right? Now, and the rocket is not working against the gravity because it is already at a certain altitude we are having some certain velocity, horizontal as well as vertical. So, and the smaller engines can be used as the path has been now inclined. Because the mass ratio and the nozzle efficiency are increased, the use of propellant, particularly such as liquid oxygen and liquid hydrogen, can be beneficial in order to achieve the high final velocity which are required for injection of a payload into the orbit. Now, this technique particularly can be challenging, but a similar concept has been applied under Saturn V. Now, what happens under this is basically Saturn V is a multi-stage rocket engine which has three stages, or particularly we can say 4 stages, where 4th stage is my payload, particularly my lunar module. I am taking an example for my Apollo aircraft, particularly Apollo 11 and lunar module, and my 3rd stage will be injection, 2nd stage and 1st stage will be my intermediate stages. Now, in order to do this, what happens? In a stage 1, we are having 5 R100 rockets, engines, which combinedly produces a massive amount of thrust in order to propel the 3 other payloads that are above one another, right? Where the first 2 do have their own fuel plus oxidizer in order to maintain themselves in a stable orbital path. Now, as soon as the stage 1 is discarded, particularly used up, what happens? From the stage 2, as soon as it gets discarded, complete structural mass goes off and stage 2 gets reignited, which again pushes stage 4 and 3. Now, the stage 2 is enough to maintain or to take care to a ratio of, to maintain or to reach a low Earth orbit. Now, in order to transfer from low Earth orbit to a lunar transfer orbit, what we will be using? We will be using this stage 3. This, what it does basically is, it pushes or it transfers, converts a circular orbit to an elliptical transfer orbit that we have discussed earlier in previous classes. Elliptical transfer orbit between Earth to Moon, right? Earth as being one of the celestial body, we are transferring an object from Earth's center of sphere of influence to the Moon's, which requires certain velocity. On that will be achieved by your stage 3. Later on, as soon as it reaches towards the Moon's orbit or in the Moon's sphere of influence, we will be creating an perigee burn, which means we will be decreasing the velocity of the rocket vehicle in order to reduce the speed and to capture onto an orbit of the Moon. Now, as soon as the object we are captured, we will be separating with respect to the stage 3, and only the 4th part, which is nothing but 4th payload, lunar orbit, is in lunar sphere of influence. Now, from there on, it's our choice where what we want to do. As of Apollo, they will be having 2 sections for a lunar module. One, orbiter, which is orbiting around the Moon, whereas the second one, which went onto the surface of the Moon and landed the first ever man in space, particularly on surface of the Moon. Next, we'll be learning a small concept regarding the strap-on boosters. Now, this is a technique that was used in Russia very early in the program that has an advantage, that the thrust of this first stage can be altered to account for increased payload without changing the fundamental design of the main rocket, right? And up to 6 boosters are used under R7 rocket, and among modern launchers, strap-on booster is a key feature that are being used. And the largest strap-on booster that are being used in the space are used on the Space Shuttle program as well as Ariane 5. The boosters are usually solid fuel, but liquid fuel boosters can also be created and used. Now, let us understand the concept. On approach to a variant of multi-stage, the calculation of velocity increment is carried out on the same ways for the multi-stage rocket. The boosters can be used to improve the performance of a 3-stage rocket, effectively making it a 4-stage vehicle, or they can be used as a 2-stage rocket engine. Now, this is a structure for my strap-on boosters, where these are my boosters that are available either by solid fuel or liquid fuel engines, and these are mounted onto my first stage. Then the first stage is directly connected to my second stage, then to the payload. Now basically it's a 2-stage rocket with strap-on boosters, or we can consider it as a 3-stage rocket. Both the ways we can consider. Or 2-stage rocket with boosters. Now, in this case, a 2-stage rocket with strap-on boosters, what happens is basically the individual boosters are mounted through either explosive bolts or through hinges, through actuators to hold them clearly onto the first stage. Now, why these strap-on boosters are necessary? Because, as we have discussed earlier, the first stage requires higher amount of thrust because it's supposed to carry the further 2 or 3 stages which are on top of it. Now, in order to make a lift off, we will be doing the boosters are ignited at the lift off and which are burned for part of first stage operation. And in modern launches such as Space Shuttle and Ariane 5, the first stage is optimized for high altitude and high mass ratio. Now, this would produce an insufficient thrust at low altitudes to lift the rocket off the launch pad, and nozzle being optimized for high altitude is also insufficient near sea level. So, the boosters provide the necessary high thrust, right? The boosters provide the necessary high thrust for the early stages of flight, particularly during the launch of the launch pad, as well as to maintain or to attain certain height. Now, when the propellant is exhausted from a strap-on booster, the boosters are separated by firing an explosive bolts, also called as pyrotechnic igniters, which drive the nose of the booster away from the rocket axis. Particularly, this explosive bolts will throw off the strap-on boosters away from the rocket so that it moves forward as the exhaust for the rocket boosters gets exhausted, although the main engine keeps it running on. So the rocket moves forward, whereas the explosive bolts will push the strap-on boosters beside. Now, the lower attachment can also be released by means of explosive bolts or maybe a simple latch which releases once the booster axis has rotated to a certain angle. Now, it is important that the boosters do not collide with any part of the rocket during the separation, and a similar requirement applies during a stage separation. Now, explosive charges, particularly springs and even small rockets, are used to guide an empty stages away from the main rocket, and there is a need to become clear when it is realized that in the period between the shutdown of first stage and the ignition of the second stage, the two parts of the rockets are essentially weightless. For a small relative velocities, if not controlled, can cause collision for the rocket. And the boosters, which generally have a high thrust, therefore a high mass flow rate, so they burn for a shorter time rather than the first stage. Let us understand this strap-on boosters concept clearly. I will explain a bit. We'll consider the same example, in what way these are staged accordingly, so that we can get a clear idea at what time they work. Now, as when you're launching from a launch pad, what happens? All the three engines simultaneously after a certain period of time are ignited. Let's say we are considering a solid rocket boosters, which upon ignition can't be turned off. Now, first, the central rocket, particularly the stage 1 engine, is ignited so that in order to check out its complete functionality. Even whenever we are confirmed, then only we are igniting my solid rocket motors. Now, as these three are working in unison, they provide a high thrust, right, which propels my rocket away or above the launch pad. Now, as the altitude increases, what we are doing, we will be, after certain altitude, we are tilting a bit, right? Small pitch we are correcting up. Now, later on, what we will be doing, as the mass flow rate, comparatively, mass flow rate for boosters is higher rather than my first stage of engines, which is a liquid fuel plus oxidizer. What happens? This can be controlled, right? My first stage can be controlled in every possible way, whereas my strap-on boosters can't be controlled. As soon as they are ignited, they work on continuously till they exhaust their complete fuel. So after a certain period of time, whenever they are exhausted, we discard basically the boosters through either by latches or explosive bolts. Now, as these are not providing any thrust, particularly the boosters are not providing any thrust, the rocket, as soon as they are split up, it continues to flow. I mean, it continues to go along the path that has been decided. So, after certain altitude, as soon as the boosters are done, they fall off. They fall off, the boosters do fall off back to the earth. Now, after the first stage, it continues to burn for a certain period of time, and after a certain period of time, it already gained some velocity, right? Now, after the first stage is done, discarding of first stage and reigniting of second stage, there will be a small time frame that is available with us, right? And let's say this is my stage where first stage has been cut off. I mean, the complete fuel as well as the oxidizer has been exhausted from the stage 1, and this is the point where my stage 2 has to be reignited. I mean, the stages has to be separated, and after certain proportion of time, particularly 1 second or 2 seconds, you are reigniting my rocket engine at stage 2. Now, during that period, what the rocket experiences is basically weightlessness. Means it also has certain velocity in which it is moving. If you are not igniting your stage 2 also, it tends to move till the apogee and fall back to earth, because it has not clearly completed a complete orbit around the earth, or it has not into the orbit. So after the stage separation and during the weightlessness, after a certain period of time, as the stage 2 separates, I mean stage 2 reignites, it tends to push the rocket towards its final orbit. Why? Because the initial mass from the boosters as well as my first stage gets cut off. So the overall mass ratio for my second stage and my payload remains very less. So by changing my type of engine as well as my type of hydrogen, but particularly fuel, I can optimize to have a higher injection velocity at that particular, starting from that altitude, right? Now, and now we'll understand, in order to maintain the mass ratio as well as the exhaust velocity, this happens under two parts. The first is the calculation is carried out for the total mass change for the two boosters. Together, the part of the first stage propellant exhausted and up the point the booster burnout. Burnout is nothing but a point at which the booster gets completely exhausted out. Means there is no solid fuel or the liquid fuel left out in a booster. and which requires an estimated amount of the propellant consumed by the first stage. Therefore, the knowledge of the burn time of the boosters and the mass flow rate of the first stage, which we already know. Now, it is usually accepted to assume a constant mass flow rate for the rocket engine as a vast majority. And the second part of the first stage, burn, is treated as in the same way, with the final mass of the first stage in the numerator of the mass ratio and the mass of the first stage at a booster burnout in the denominator. The second and third stage mass ratios are calculated in the generalized usual way. Now, another concept, particularly a payload shroud or a nose cone, is needed during the early part of the flight to protect a payload from atmospheric forces. Right? Payload shroud is nothing but a cover, also called as nose cone, is needed in order to protect the payload from the atmospheric forces during the launch as well as till the atmosphere remains. As soon as the rocket is out of the atmosphere, we can discard the nose cone to save some structural mass. Now, at low altitude, these are common forces, particularly lift as well as drag, which are experienced by the aircraft, and as a result for which required a streamlining. Now, whenever we are launching a rocket, we can't launch a blunt face, particularly, right, onto rocket, because there will be a sufficient amount of backward force, particularly drag, onto the rocket. In order to require this, what we'll be doing, we will be streamlining them, right, also called as my nose cone, right. As soon as the air goes through, it deflects itself. As the rocket goes, it deflects. Now, till what extent? Until unless there is something present. As soon as there is no air left, you can directly discard this nose cone in order to reduce the overall structural mass. Now, at higher altitudes, particularly, the rocket has reached the high velocity, which is much more than the speed of sound, while the air is now very thin. So, the rapid motion of air past the nose can now leads to heating. So, all these effects will damage the payload or require it to be made strongly than consistent within its use. So, all the launchers have a shroud around the payload to protect our payload, and a payload can be a satellite or a spacecraft. In fact, attached securely to the top of the last stage motor, particularly second or third stage in our case, and the shroud is mounted around it. If I'm considering this as my last stage motor and this is my satellite, that will be my payload shrouding. As soon as it gets out of the particular area, particular altitude, it gets discarded. Then it will be directly flowing onto the vacuum of space. Now, for heavy launchers, it also has to provide for large enclosed volume in order to allow the larger spacecraft to be carried, and which generally leads to a requirement of composite construction of shroud to minimize the weight but maintain structural integrity. Why? To protect the payload, right? And based on all this, what we'll be doing, every rocket, if you're considering for a single stage or a multi-stage rocket, what are the components that it's supposed to have is a rocket motor plus fuel plus oxidizer, particularly in terms of tanks, in form of tanks, plus payload enclosed in shroud, particularly let's say on nose cone. right? These are your basic stage for a single stage or single rocket motor engine. Now if you are putting for multiple stages, these we are adding up in terms of stages, then the payload remains as it is, right? And with this we'll be concluding your module 1. Next we'll be continuing with your module 2, where we'll be discussing about in a mathematical forms regarding the rocket principle and all the other terms related to your rockets, particularly principle of rocket. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.